Okay, so, sorry. Chapter 17 is due tonight.
Yes.
Any questions about that at all? In the slightest?
I know you said on Tuesday that it was due on Thursday, but that didn't register, so I did it so that it was due on Tuesday.
I mean, better that than the other way
Have
around.
y'all done the quiz already?
Yes.
I'm gonna be honest with you, Pop Pop. I opened both things. I opened the homework for the first time this morning.
Okay.
Not a great reflection on my work ethic, I know. So I don't have any questions for you because I haven't seen the last half of it yet.
Fair.
I don't understand how to do the potential difference when there's multiple things.
Okay, great question. Referring to, say, number 8, or is there a different one?
Well, no, because I got that. I was more looking at number 2 on the quiz, because it was like with the light bulbs and it was the difference in voltage.
Right, so since that's the quiz, I'm going to put up a similar problem.
Yeah, that's not, like, I just don't understand the concept.
Well, yes, absolutely, happy to go over that. That's not bad menu. All right, so we're going to look at number 8 on the homework. This is a combo circuit. Everyone will have 2 slightly different resistances and 1 different voltage on it, but 3 of the resistors present are the same for everybody. And conveniently, I feel, the first 4 parts of the question are just helping you work out step by step what the total circuit resistance is. So A through D takes you one piece at a time, simplifying the circuit from the inside out till you get the overall total resistance as the answer to part D. So stepping through those, exactly where you want to start. And if for some reason you aren't getting those ones right, if you're trying your best, it's just not giving you the right answer, please do talk to me before you try the rest of them, because you do need part D correct to do the rest of them. So D ends up being total circuit resistance. Just combine all the resistors together to get that one total resistance. And then part E asks current through the battery, which is also the current through the entire circuit. So using the total resistance from part D, this whole thing amounts to just one ultimate large resistance. Current comes out of the battery, travels through the whole circuit, comes back to the battery. So to find, it's a letter after D, E. So total circuit current, V equals IR. V total equals I total times R total. That's all standard stuff up until this point. But after D, we now have to start looking at elements of the combo circuit specifically. E, you just found the total current to the whole circuit. F, we are now asked what is the magnitude of the voltage drop across R2. So if we look at the circuit as a whole, current is going to come out of the battery. All of it has to travel through R2, because R2 happens before anything else. So the total current from the battery is going to pass through R2. Then that current will split here. Some of it will go through the 3 ohm, some of it will go down this convoluted looking branch before it all comes back together here and then heads into the battery. So part E was total circuit current, excuse me. Part F, we want to find specifically the voltage at R2. looking at the circuit, sorry, this is read F. If we care about what happens at R2, we need to use the variables that R2 is specifically dealing with. So to find the voltage at R2, we need R2's resistance and R2's current. Now, because of where R2 is in the circuit, and we just sort of track the current as it flows, what should the current passing through R2 be?
Equal to the total.
Equal to the total. So far, R2 is just in series with the battery and nothing has happened first. So, the answer you found for E, the total current, is R2's current. So you can use that number with R2's resistance to find its voltage drop. And the sample numbers and sample answer here give us 4.63 voltage drop across R2. Notice that is smaller than the battery voltage. It has to be because this total voltage is going to drop sequentially in bits across each of these smaller resistors. So this is how much of that 7.5 is going to drop across R2. I'm just going to do a quick tally. We had 7.5. We just dropped 4.63. That's going to leave us with, I can't do mental math all of a sudden.
It's okay, I can't ever.
It's slightly less than 3.
That look right? I'm a math minor, and I'm incredibly dependent on my calculator now. Okay,
So is that the answer for G?
ultimately, yes. Yes, I did it right. Now, part F asked us to find just the 4.63 using the numbers on the board. G then goes on to ask, well, if the 4.63 was the voltage drop across R2, what then must be the voltage drop across the 3 ohm resistor? So looking back at the circuit, current is going to go through R2. The current is then going to split. Some of it will go down this branch, some of it will go down this branch. So each of the opposing branches will get different amounts of current. But since we've broken into a parallel circuit, each branch will get the same total voltage drop across the whole branch. And after that first resistor, it went from 7.5. After this first resistor, we have dropped to a remaining voltage of the 2.87. That's kind of the voltage that's left after that first resistor dropped it.
Why are you subtracting?
Total circuit voltage. This is how much dropped across resistor 1.
So that's the answer to F, is the 4.
Yes.
Okay.
When you work F, solving for voltage drop across R2, you get this number. This number is what's left after the drop across R2. So we went from 7.5, we dropped across R2 to 2.87. Now, from here to the end of the circuit, that 2.87 will drop to 0. The question is just, from here to the end, what would the voltage drop across the 3 ohms be? And since immediately after R2, we hit parallel circuit territory, whatever the remaining voltage is right after R2 is going to be applied to both branches of this parallel circuit. because voltage doesn't split at a parallel. Current splits because electrons can only go one way or the other. But voltage is like water pressure. And if you split a hose, the water pressure is still pushing down each side. And voltage only drops across a resistor. So along this pathway, we're now at the 2.86, 2.87 remaining. We don't hit another resistor until the 3 ohms. And then since there's no resistors after it, we must have gone from 2.87 to 0. Because it has to be 0 before you get back to the battery, and there's no more resistors to drop it across. So, that remaining voltage is applied to both branches, and since the 3 ohm is the only thing on that branch, it gets the full remaining voltage. Once we determine that, we can do, part H asks for V equals IR again, but using the data for the 3 ohm resistor. This makes, combo circuits are kind of like puzzles. Look at each piece one part at a time. And because of that, there's not really a standard model for any of them, because they're all different. You have to follow the current through them in different ways. But between WebAssign and test questions, I'm never going to ask you to do anything. Any requests I make involving combo circuits are going to be reasonable. Because the sheer amount of time it would take to analyze every single part of that circuit above and finding the drop in the current for every single piece of it would take forever. And if that was a test question, it wouldn't be fair because you have the whole rest of the test to take. So for any combo circuit, finding total resistance or total capacitance in a combo is a fair question. And maybe finding certain pieces of like voltage or current for certain parts of it that are easily accessible would be fair game on a test as well. I want to talk about this question because there is one similar to it on the quiz. Not exactly the same, there's fewer resistances. Quiz question, so it's meant to take a shorter amount of time. But employ the same logic when looking at how the current will split in parallel, but the voltage won't. Any questions at all about, well, let's start. Any questions at all about homework number 8?
Do you have staplers?
Staplers are an endangered species. If you have paper clips,
I have a paper.
you may. Any questions about Chapter 17 assignments at all? Okay. Again, while working on homework or quiz, find me in the building, email me questions at any point about, did I do this part right? Because the rest of the question kind of depends on it. Please, 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 don't hesitate. If I don't answer, it means the only reason I won't answer is that I'm asleep. Or maybe driving. Okay. I'd say that's a good segue point, kind of a pause point, because I'm going to clear the board off and put up a couple of magnets things. It'll need a second for water, etc., or just a break. Now's a good time. Just going to go ahead and write some things down so I don't have to do it while I'm talking. That's the same.
The heat capacity for water is 4,186.
Yes, it is. Questions before I resume? Okay. We have already started the magnetics notes. I've edited a few things, so we'll be jumping around slides to add additional information. We're also kind of jumping between chapters at this point in the semester. We just did 15, 16, 17. I kind of took a few elements from what the textbook would say is chapter 18 and added them to 17, just to get all the resistances stuff together. And we're skipping the rest of 18 and jumping to the magnetic fields part of 19 and 20. So we're cherry picking, I am cherry picking the parts that I feel are the most useful to you guys to exist as humans on planet Earth. So we're talking about magnets because despite how magnetically mysterious they are important and they are everywhere. And after the magnets chapters, we will review all the electricity and magnetism stuff, have one more normal test, and then we will spend the next couple of weeks before the exam talking about waves, which are also important to our existence as humans, and also reviewing for the exam. So, jumping around to important, useful chapters at this point. What we are calling Chapter 19 contains a little bit of Chapter 22, like the magnets. And the magnetic force is what's known as a field force, which you could describe rather circularly as forces exerted by fields. It's not a great definition because you're not supposed to use the word in the definition. So a slightly more divorced from the original words definition is a field force is any force that can be exerted over a distance without physical contact. Two things touching can exert forces through fields at each other, but they don't always have to be. If you ever played with magnets as a kid, pretty sure you pretty quickly found out that they can pick each other up from a distance, and that is because the fields interact with each other from a distance away. Why are these not? And this is the third type of field force that we have talked about. We already compared gravity and electrical forces together. Magnets are a different type of field force. And it's a field force because there is a magnetic field that creates the magnetic force. And typically speaking, one type of field only interacts with itself. Gravity doesn't interact with either of the other two. Only very specific cases have electric and magnetic interacting, which we've already talked a little bit about. But these all categorized as field force, and to my knowledge, that is the list of main field forces. Maybe the nuclear forces count in that some subatomic particles don't need to be touching to exert forces on one another, so they might count. I just don't know a nuclear field off the top of my head. So, magnets create magnetic field. We talked about that briefly. Talked about Earth's magnetic field that helps to deflect space radiation, which is just very convenient. And the weird quirks about Earth's magnetic field, such as the fact that the geographic North Pole is closer to the South Magnetic Pole, because very strangely, not only does Earth's magnetic field moves. Our field kind of works as if there was a giant bar magnet in the center of the Earth, and occasionally that bar magnet just kind of wiggles around. So the spot your compass points to changes with time. It won't always be pointing at the same geographic location. I think right now the magnetic pole is closer to Alaska than it is to the middle of the Arctic. It's at least drifting towards Alaska. Meanwhile, the South Pole, which is actually magnetic north, is drifting away from the center of Antarctica.
So what if Santa actually lives at the South Pole because it's the magnetic North Pole? We've been looking in the wrong spot.
Maybe. That would be a very long, well, assuming that Santa Claus is St. Nicholas or a similar person of European descent, getting to Antarctica would have been tricky. Then again, you could fly.
But it'd be better than floating in the middle of the ocean, because I always thought there was like a landmass up there that Santa lived on.
I mean,
Because we
the
said
North Pole, the North Geographic Pole is a giant ball of ice. So there
Okay.
is terrain to stand on. It's not
I
ocean.
didn't know.
Weird thing though, the term Arctic, you guys know the definition of Arctic? Arctic comes from the word arctos, which means bear. So the Arctic is the pole that has bears, and the Antarctic is the pole that doesn't have bears.
That's so funny, I love it.
Yep. But polar bears only live at the North Pole, the Southern Pole has penguins instead, and leopard seals.
Wait, what lives in Antarctica?
Antarctica has penguins and leopard seals. You do not see those at the North Pole.
You don't have penguins at the North Pole?
No.
Really?
I'm pretty sure all native penguin populations live in the Southern Hemisphere.
What? What?
The closest thing to a penguin you will naturally find in the Northern Hemisphere is a puffin.
Oh, I love puffins.
Okay, so currently magnetic north is actually the South Pole, except it wasn't always. There's geologic evidence that occasionally, not only do Earth's poles kind of drift around slowly, sometimes they just flip-flop.
Do you know there's penguins in Australia?
Yes, I have
And
heard that.
like tropical places?
Yes.
Look
I
at
think
this.
there's some in South America too.
There is.
Yeah, there
Like
is.
all of Chile has penguins.
Oh, I didn't know they went that far.
Dude, they're like by Mexico.
They look very different. They're sandier.
I'm looking
So
at
not have to
Mexican
blend in
penguins.
with snow. They're less white and more sand colored.
This is what happens when I look up Mexican penguins. That's not cool.
Is it a club penguin with a sombrero?
Yes, it's like a bunch of sombrero penguins. That's not what I wanted.
So when the Earth's magnetic field just kind of switches, which it has done in the past.
We believe it has done that in the past, not because humans have observed it happening, but because you know how Earth's tectonic plates are slowly either being subsumed on one side and generated on the other, and how slowly new crust comes out of one side and I assume gets submerged at the other side.
Okay.
We've examined the seafloor remotely because it's scary down there. And as new crust is formed and coming out of, what's the word? Not fissures, faults. As new crust comes out of those fault lines, the magnetic particles and like iron dust in that rock sets in a certain direction based on Earth's magnetic field at the time. Because when the magma is liquid, the particles just align themselves before it solidifies.
Okay.
And we've noticed bands, like this band here, all the particles point that way. But then this next band next to it, they all point in the opposite direction. And then, you know, however amount of time later in the next band, they all point that way, and then the next band, so back and forth. So it looks like the poles will flip-flop arbitrarily every couple of epochs. This leads to the assumption that besides the fact that the poles drift and can apparently flip directions, indicates and created the main theory, really the only theory as to why Earth has a magnetic field. And we believe it has something to do with magma in the core and or the mantle. Because molten iron flowing through the core should create a magnetic field. And since it's a liquid and it's flowing chaotically, if a change in the flow happens, that would cause the poles to drift and maybe switch. The inversion part is still really weird. We don't have a good answer for it. But right now, our only working theory for why this planet even has a magnetic field in the first place is molten iron in the core, or around the core.
So not all planets have magnetic fields.
They do not. And planets without magnetic fields tends to be barren hellscapes because solar radiation blasts their atmosphere away, like Mercury. Yes. Hang on.
Mars and Venus do have magnetic fields.
Yes.
Jupiter, Saturn, Uranus, and Neptune have magnetic fields stronger than Earth.
It's probably why they're, well, that and distance from the sun is probably why they're very cold.
Does the strength of the Earth's magnetic field change, or is it just the same?
It appears to be roughly constant.
Okay.
Then again, shifts in it might explain ice ages. Because if the field got stronger, it would block more radiation and we'd get colder. Meanwhile, Mercury's magnetic field is 99% weaker than Earth's, which is why they have no atmosphere. And that's why the daytime side of Mercury is 8 squintillion degrees, and the
Why does
nighttime side of
magnetic
Mercury
field
is
equal-
frozen solid.
Why does that make an atmosphere?
It's not that the magnetic field makes an atmosphere. The magnetic field protects the atmosphere. It's good that we have a sun. We'd freeze to death without it, but without our magnetic field, it would also kill us. So if you were to look at a map of like radiation through our solar system, it would look something like this. The sun is literally bombarding us. Earth has always had an atmosphere, and the magnetic field is the only reason we still have an atmosphere.
So it's like a force field.
Yes, quite literally. It's a force
It is a
field.
force field.
Field forces
Oh.
can act as force fields. Gravity doesn't really do that though, because there's no such thing as repulsive gravity that we're aware of.
Could
So-
you do that, like, on a small scale, make a magnet force field?
Yeah,
Has anyone done
well,
that?
I mean, we have it on this scale, which is kind of small on a cosmic level.
But like, on a really small scale?
Is that how like magnetic trains work?
Kind
Is
of.
there like,
Maglev trains use you turn on the electromagnet. The magnets are designed so that the field points in a specific direction to reduce friction, and then points in a different direction to push up and forwards at the same time. But those are electromagnets so that you can turn them off. Hypothetically, we could invent like it is possible to create like, to wear an electromagnet that creates a field strong enough to bounce bullets off of.
Have
But-
you done that?
I don't know if anyone has actually done that in real life. I once saw a Batman sketch where he did do that.
You should do it. Be the
Well,
first.
The Batman sketch showed a few of the problems with it. One, it would take a ton of power. Either you would have to carry around a magnet that is always on, like a normal bar magnet, and in that case, you're just constantly exerting a magnetic field that will cause everything around you to go haywire. Alternatively, if it was an electromagnet that you could turn off, it would be bulky and cumbersome, it would take a huge amount of electricity, and even if you could turn it on before the bullets started flying, there's no guaranteeing what direction they're gonna go in.
So it could pull it towards you and you get shot harder?
If the poles were wrong, yes. If the poles did reverse it away from you though, it could go into a bystander, which is why Batman doesn't use it anymore.
so he killed a bystander?
A bystander got
Shot.
grazed, a bystander was bleeding, so Batman stopped the fight, ended the fight, took the bystander to the hospital, and then broke the magnet. No guns, no bullets. Okay, so magnetic field important, and apparently the radiation from the sun does kind of like create that comet blasting effect. And the magnetic field and Earth's radiation, the sun's radiation is also what creates the auroras. Since the field lines are coming out of one pole and going back into the other, the field is just stronger at the north and south pole. So when radiation from the sun hits the north or south pole, the radiation is so strong it creates light in that interaction. So the auroras, either
So is it-
northern or southern, are this is what happens when radiation hits our magnetic field.
So it's like how you drew like the lines and you have the plus and it moved, is
Mhm.
like that's what's happening?
Yeah, when that happens, there's so much energy involved at the pole, like when that happens at the north or south pole, there's so much energy in that collision and that interaction, it gives off light.
Okay.
And this is also one reason why the poles are just naturally colder than everywhere else on Earth. You know how the Arctic or the Antarctic goes through points of the year where they just have direct sunlight 24 hours a day?
Yeah.
You ever thought about how it's still frozen up there that time of year?
No.
Up until this moment.
The magnetic field just blocks more of the heat up there. So even the light gets through, like visible light gets through to where you can see, but all the energy gets absorbed by the field and it's just physically colder. Meanwhile, it's weakest at the equator, so it's warmer there.
The magnetic field is weaker, I think.
Yeah, the field lines are further apart.
So could that have any function on like people's like bodies? Like are people's bodies different closer to the poles?
I mean, you would have to be pretty well adjusted to the cold. You would get less radiation, which might make you less healthy.
Radiation's good.
Most things are good for you in low doses, and that includes radiation. That's why some people who live on top of mountains are actually healthier than us sea level dwellers, because being higher up, you get more of the radiation that makes it through the atmosphere. Also, you'd be acclimated to low pressure and cold, which would just make you hardier in general.
It's a shame I'm a beach girl.
Nothing wrong with it, you're just adapted to different circumstances. You have your strengths. Surface dwellers would probably find it, mountain dwellers would probably find it too hot down here, and the air too thick.
We really do breathe like in Charleston, we're like breathing water.
Yes.
Because like if you go somewhere and then you come back, you're like, God, the air is so watery.
I worked near Orlando one summer, and every time I went outside, I felt like I was swimming.
Yeah,
Least of all because it rained constantly.
that's true. Sun showers in Florida are on the rare.
It didn't only rain water. Once or twice it rained snakes.
Snakes.
For some reason, the campus we were using, there was just a bunch of like bug-eating snakes that would climb up trees to get bugs, and then gravity did its thing.
Oh my gosh.
That happens here sometimes too.
Oof.
That's
I've only
where
seen,
you go rat
I've only
playing
seen
right
inchworms
outside.
fall out of trees here.
They're usually going for the squirrels though.
They have squirrel-eating snakes in this town.
Yeah.
Interesting. Hadn't seen that
Well,
one.
in the upstate.
Ah.
How about that?
I can count the number of snakes I've seen living in South Carolina on one hand.
Really?
Meanwhile, I've seen, most of the skunks I've seen in the world have been in South Carolina.
And then I never see armadillos here, but as soon as you go to Florida, there's like a million armadillos.
I really
Where do
want
they
to
come
try
from? They don't cross the border.
We also have armadillos here.
I'm sure we do, but I have never seen one.
Sadly, I've only seen them as roadkill.
I don't even see dead ones. I just only see them in Florida.
Florida, Texas too. But
I mean-
even though like technically they do live here,
If they're native to the desert, Florida's just the humid desert. Right?
That's fair.
it's extreme, but on the other end, it's like very dry. It's very dry.
We have discussed how charges have to be moving through a magnetic field in order for the field to exert force on them. It's because they exert different types of fields, and they only really interact because of a glitch. And that glitch is caused when there is perpendicular motion between the two. And the formula for that is what is on screen right now. Label these terms. F stands for magnetic force. I almost wrote magnetic force on charged particle. Because it's a force, it is still measured in newtons. For the magnetic field to be able to exert a force on this charged particle, the particle needs some amount of charge, so Q is still charged, still measured in coulombs. The B is the variable for magnetic field strength. So in all of our formulas, big capital B is magnets, magnetic field.
What is the unit on that?
That's a wonderful question. It's probably not going to make you happy. Magnetic field is measured in units of Teslas.
What are units of a Tesla?
Well, 1 Tesla would be equal to 1 Newton second divided by coulomb meters.
That sounds horrible.
It is. It is horrible. It is the standard metric unit for magnetic field, and I don't know off the top of my head what else it converts to.
I dislike it already.
Equivalent unit for Tesla. Which one would that be? Car at? Tesla is a standard unit of magnetic flux density, equivalent to 1 Weber per meter squared. Okay, no. There's a better unit now. We've got 1 Tesla is 1 kilogram per 1 amp times 1 second squared. So we don't always know why magnets do what they do, but we at least know what they do and we can measure it. So we have a unit for magnetic field strength, like we have units for electric field strength. And the last variable in this interaction is the velocity variable, but I'm going to highlight that it has to be perpendicular velocity. The particle has to be moving perpendicularly to the magnetic field lines. If this proton were stationary, nothing would happen. If the proton were moving in the same axis as the field lines, nothing would happen. It is only perpendicular movement that causes the glitch that creates a magnetic force on an electric particle, which is why when making generators in lab, the magnet had to be moving to produce electric current. Technically, the particle could be moving perpendicular to the field. Also, the magnet could be moving perpendicular to the electron. So if velocity was 0, force equals 0, the particle will move unimpeded. It is only when you have a perpendicular velocity that you actually get a force out of this. And we talked briefly about the right-hand rule that helps determine that direction. If you would like a written definition, like a textbook definition, if the field and the velocity have to be perpendicular to each other, and the force will be in the one axis that is perpendicular to them both. So for example, if the field and the velocity are in the x and the y, that would put the force in the z.
So the force is always perpendicular to whatever plane of magnetic field and velocity are in.
Correct. That is a good textbook definition of it. And the right-hand rule is a good, quick way to be able to tell. That said, the right-hand rule is calibrated for protons and positive charges. Technically, an electron would do the opposite. So for the electrons, consult the left-hand rule.
Wait, what?
Okay, quick sample question. Let's just look at the situations I've drawn here. These two create no force, because the vectors aren't perpendicular. This would create a force. It is a proton. So using right-hand rule, fingers point in the particle direction, the field points in the palm's direction. So for this proton in this field, the net force would point into the board. If this was an electron, it would go in the opposite direction, because they always do the reverse of each other. Which means that with my left hand, fingers pointed up, palm pointed forwards, my left hand shows where the electron would go.
So it would go that way?
Yep,
So the opposite of proton.
correct.
Which makes good sense.
Sorry,
Which makes good sense.
it makes good sense. So if right and left are tricky, you can write proton on this palm and electron on this one.
Take a proton at the stop sign.
So for this proton, the field is going to point into the, the force will point into the board. And we haven't done a whole lot of three-dimensional drawings or graphs in these classes because our boards are flat and none of the work physicists here are artists. But because there are now three axes at play, there needs to be some standard way to show some dimensionality coming into or out of the page. And the shorthand for that, for those symbols, is, if you look on the screen here. Right now on screen, these dots and these X's represent magnetic field lines. The X's represent lines pointing into the page. Like you just shot an arrow at the page and you can see the feathers on the end of it. So for this question, if we were asked to draw the force vector and it was supposed to point into the board, an X represents it as pointing in the negative Z.
What about coming out?
Great question. So I'm going to use purple for this electron because my blue markers have all died. Electron would, the force on an electron moving in the same direction would be opposite this one. And instead of the feathers of the arrow as the arrow goes into the board, this is the tip of the arrow pointing towards you as it fires out of the board towards your face. Some people just use the dot instead of the circle and the dot. But X for in, circle, dot for out. So for both of these examples on screen right now, this is magnetic field coming out of the board, positive Z-axis. This is magnetic field going into the board, negative Z-axis. And quick sample magnetic right-hand rule practice. We're told particles involved in these are both protons. So we use the right hand. For this first one, proton begins moving in the positive X, and the magnetic field is pointing out of the board. So as this particle enters the field, the force is originally going to point down. But we start entering centripetal force territory at this point, because the force is now going to point down. The particle is going to begin accelerating down, but it already had forward momentum. So it's going to move forward and down at the same time. Now its velocity points on a slant, and the force is going to continuously keep changing direction with the velocity, creating a cycle. That's like centripetal force did. So if you've got one particle trapped inside of a magnetic field bigger than its radius, it's just going to spin in there forever. Which is one reason why the generator works, because the spinning magnetic field causes the electrons to spin through the coil. They'll travel along the coil until eventually the coil leads them out of the field.
Okay, so what if someone had cancer and you put a magnet around their cancer and then gave them radiation?
Well, see, I'm under the impression you usually shoot radiation at cancer cells because you want to hit the cancer cells.
Yes, correct.
The magnet might interfere with actually hitting your mark slightly, because the magnetic field might deflect the radiation partially. It's not a very strong magnet, I assume. Magnet would only do this to like particles, to charged particles, not to. I mean, a strong enough magnet might make a photon and might do this. It's kind of how you end up with black holes. Have a great day. Okay. If you were to take like one of these things and sew it into a person, that wouldn't really work for this, because this one object is equivalent to a bar magnet, which means that its field lines are constantly changing direction.
What if you had a ring magnet? And then you could just have a particle keep going through till all the cancer is gone.
Maybe. But at that point, you're just installing a machine that just sends the tumor into a blender, basically.
But I mean, that's what radiation does anyway.
I was under the impression the radiation just killed the cells.
I mean, it's for like localized, it destroys the cells and then your body eats the destroyed cells.
Right. And the goal is to not have to perform surgery.
Or chemo, unless you do
To put the magnet into the person, you have to be cutting into the tumor anyway.
both. That's a good point.
Additionally, you'd have to be spinning their own electrons around unless you shot new electrons into them. So basically electrocuting them. None of these really sound superior to any of the existing options, in my opinion. Surgery followed by electrocution. Maybe both at the same time. Excuse me.
My thought is like, put it in, like this is the cancer, put in a round magnet and then give them radiation, then just spins around in there until it's all dead and then take it back out.
It would have to be a really strong magnet to make radiation start spinning in a circle. And after, a magnet that strong would probably have other side effects. Because no magnet you've ever interacted with on Earth's surface is strong enough to deflect radiation. Earth's magnetic field can, but that's the only thing we've got on that scale.
Gotcha. Okay, well then next my idea. Next.
I like the thought process, if this was, that's like the high-end sci-fi stuff that I like, because as soon as I learned how wormholes work, I wanted to open one and use it for teleportation. It's just the practical mechanics of opening a wormhole takes more energy than exists on this planet. Like how the magnet in question also doesn't exist on this planet,
Would
to my
it
knowledge.
exist on another planet?
That's what SpaceX has been trying to do then. Go to Mars for super magnets.
Yes.
Superman, safe Superman.
Safe super magnets. The
Yeah,
cure for
we're gonna
cancer
cure
is
cancer.
on Mars.
It is,
And
Reddit.
and Elon Musk is trying to privatize it.
probably.
So why are some things magnetic and not all things?
Are you asking why do bar magnets make magnetic fields, or why do only certain things respond to magnetic fields?
Second one.
Second one. It's a great question. It's one that I don't have all the answers to. I am under, what little data I have tells me that particles are objects that respond to magnetic fields. One of the common terms for that is ferromagnetic, named after iron, since it's the main thing that is ferromagnetic. The particles in that object respond to and orient themselves along magnetic field lines, and the force will then cause them to follow along those lines. Being exposed to a magnetic field makes those objects a little bit magnetic themselves. For a moment, it will start giving off its own field, and that field it makes interacts with the original magnetic field, and when fields overlap, you get force. You might have noticed something like this if you ever had a magnet, put it on one end of a nail, and then the other end of the nail you can stick staples or paper clips to.
Yeah.
The iron itself in the nail is not normally magnetic, but being exposed to a magnet sort of aligns its protons and neutrons protons and electrons in such a way that it makes its own magnetic field, or it is induced to have a magnetic field for that moment of exposure. And that's why when you remove a bar magnet from the nail, paper clips all fall off. Because the other magnet's the only thing keeping it magnetized. Certain materials
Okay,
are just
new
able to
idea.
do that.
What if you took something that was not all the way, wasn't normally magnetic, like iron something, and you put it around the cancer, and then you magnetize it, and it went, phew, and it just went like that, and then squished the cancer.
I don't see how that's any less physically traumatic than surgery.
But if you can't get it out with surgery,
But you can install magnets.
yes.
This is interesting.
This is sounding like a very improbable edge case. I can't think of a scenario where you couldn't make an incision to pull the cancer out, but you could make an incision to put a magnet in and then leave it there.
And then eventually remove it.
And hope that it doesn't crush
The
itself
magnet
against.
cancer ball needs to be removed.
You also don't want any of the magnets you put in to slam into each other and crack, because then you've got just fractures and slivers of the metal in their body. I've had really strong magnets that I got at Lowe's, and I had to be really careful with them because if I held them about this far apart, they would pull towards each other, and at the final top speed that they reached, it was strong enough for them to break.
What about those ones that you can get at the gemstone store? What are those? That are
Magnets?
yeah, they're
Are they shiny silvery?
yeah.
Those are probably made of neodymium. A neodymium magnet or a rare earth magnet is just one of the strongest naturally occurring magnetic substances on Earth.
Are you talking about
And they go,
you throw them in the air and they clatter? I have 7 of those in my room right now.
Nice.
They're stuck to my wall.
Oops. I think it's too
I have them
strong
on
stuff.
my fridge.
No,
I use them as fridge magnets, which is
yeah.
dumb, but
I just have them up high enough so that my cat won't mess with them.
I've got a bunch of stuff stuck to my file cabinet with these things, but they're so weak, it takes 8 of them to hold up one corner of the page. These things, like this common type of black magnet is made out of iron clay. And you can make something that's made out of iron have a magnetic field if, when you are pouring the iron and before hardening the object, you expose it to a magnetic field. That permanently locks its particles in such a way to keep making the field.
I was wondering how they made mine.
On the
Thought they
other
ground
hand,
up magnets and sprinkled them and stuff.
on the other hand, when forging something, you can also force the iron in it to not respond to magnetic fields, which is why a lot of steel isn't magnetic. You don't really want a bunch of your implements to be magnetic lest they fly away due to a magnet being nearby. Very famously, most steel swords and weapons have, like, the blacksmiths go through this process to align, make sure the particles don't align to a magnetic field and can't align to a magnetic
How did
field.
blacksmiths know how to do that?
Over 2,000 years of trial and error.
My dagger is made from a railroad stake. Yeah.
Probably
railroad
still
stake.
magnetic
And
then.
it is very magnetic.
Okay.
It's also really sharp.
Like in ye olde Beowulf era England, I don't imagine there was a whole lot of issues if your sword was magnetic. But as time went on, it became more of a problem. Who knows, there might have been a wizard whose trick was just, I have a magnet and now you don't have your sword.
So we started time traveling with things that we should bring with us are strong magnets,
Strong magnets,
ibuprofen,
ibuprofen, antibiotics.
those little ice packs where you like punch them and they get cold.
Chemical reactions in general. You could scare a lot of Beowulf era peasants with a flame test.
Elephant toothpaste?
Ooh.
People would think you're like freaking crazy.
I would also go with an electric lighter, not one of the gas ones because you can run out of gas.
You would also want to bring a hand crank electrical generator or a solar panel.
And go solar panel.
I used to have a crank TV,
Ooh.
but it would only last like